All right, class, today we are learning about inverse functions. Just a super forewarning here. When I'm talking about inverse functions, I'm not talking about the relationship like x and 1 over x. It's an inverse relationship, yes, but what we're talking about is the relation between two functions. So if we have f of x, then its inverse is written as the inverse of f. So it's got that -1 superscript up there, but we would say that's the inverse of f. A couple pieces of information you're going to need here is that two relations are inverse relations if and only if one relation contains b comma a whenever the other relation contains a comma b. Like, so just switch the x and y values and compare them. We've actually talked about this already. Graph of a relation and its inverse is actually just a reflection across the line y equals x. That's the perfect diagonal line across your graph. So to find this inverse graphically, you're going to pick some points on the graph and just literally switch the x and y values because it should reflect that function or that relation across that diagonal line. All right, so let's look at the graph of an inverse function here. We have f of x's table, which means that the inverse of f's table is just literally all of those points switched x and y. So instead of -2, -1, we have -1, -2. Instead of 0, 3, we have 3, 0. Instead of 1, -3, again, just switch the x's and y's, and we do that across the whole table. If we want to graph this and see what it looks like, we'll go ahead and draw our perfect diagonal line across our graph. Let's make sure it's nice and neat. Okay, and then let's plot these coordinate points. So f of x's first coordinate is -2, -1, and the inverse of f's first is -1, -2. You see how those dots, those two coordinate points, are perfect reflections across that diagonal line? That's good, since these are inverses. Our second coordinate is 0, 3 for f of x, and for the inverse of f is 3, 0. Again, perfect reflections. We have 1, -3, and so we have -3, 1. Perfect reflections. And last but not least, 4, 2, which means we have 2, 4. Again, a perfect reflection across that y equals x line. Moving on a little bit, we want to be able to check and see if we know how relations are related to each other. Inverses and functions are related to each other. And we can check that on a graph pretty easily. The inverse of a relation is a function if and only if that given relation passes this horizontal line test. So we've been doing vertical line tests for like our entire life to decide if something's a function or not, but we can employ the horizontal line test with pretty much the same rules to decide if the inverse of that relation is a function. So that's what we're going to do. We're going to decide if the relation is a function and if the inverse of the relation is a function. In the first one, if we use the vertical line test, it's going to be able to tell us if we have a function. This passes the vertical line test because we can draw a bunch of vertical lines on this cubic function here, and at no point do any of those vertical lines touch the graph more than once. So since it passes the vertical line test, we would say f of x is a function. And then we switch, and since we're also going to be answering the question, is the inverse of the relation a function, we now employ the horizontal line test. But hopefully you notice that immediately that horizontal line test is a fail because it touches that particular horizontal line touches the graph 3 times. So we know that the inverse of f is not a function. Plain and simple. If we do the same thing for these other two graphs, first with the vertical line test to decide if the one shown is a function, this passes for this rational function, so we know f of x, the one shown, is a function. And then we look again with the horizontal line test, and since at no point horizontally do any of those lines cross that graph more than once, we can also say that this passes the horizontal line test. So we know that the inverse of f will be a function. We don't have it shown right now, but we could reflect that across the line y equals x and get a function. For the third one, this fails the vertical line test, which means that the one shown right now is not a function. So f of x is not a function. However, if we checked that horizontal line test, it passes. There's not a single point where a horizontal line is going to cross that graph more than once. So it passes, which means that the inverse of f is a function. Pretty cool. Now, we're also going to want to be able to find the inverse of a function algebraically, because we're not always going to graph it. And that way we can write a function, like we can write an equation for the inverse. One thing we need to know before we get started is that the range of f of x is going to become the domain of its inverse. Since domain and range are switching the x's and y's, it makes sense that the range of the first one becomes the domain of the second. So the first thing that we're always going to do before we find that inverse function is we're going to look at the range of the original function, f of x. So I've already written an example here for you, and we've checked the range. The one given to us is a cubic function. So if you remember what a cubic function looks like, it's something like what I've graphed here. And a cubic function has no restriction on its domain nor its range. Its range goes down to negative infinity and up to infinity. So this already I know is going to be the domain of my answer. Like we've already figured that out originally. Doesn't make any sense kind of right now why we do that, but you'll see an example when that happens. So I just want you to look at my work here. So first things first, I changed f of x to y, because if we're switching x's and y's, I want to make sure we know what we're switching. And then we did truly just switch the x and the y. But I want to resolve the equation for y. That's here in my instructions. So you switch the x and y and then resolve the equation for y. I would have subtracted 2 to both sides. Here, I'll annotate it for you. Minus 2 minus 2. That would be x minus 2 equal to y cubed. I'm going to cube root both sides. So that is the cube root of x minus 2 equal to y. And that's my inverse function. But I have to make sure that the domain that I answer for this inverse function is exactly the domain, or the range of f of x. I've already done that part, so I don't even have to think about the domain, because it's the range of what I started with. So I want you guys to try B. Pause the video right now before I get started talking about it, so you can also tell me about this function. Okay, so if we're looking first at the range of f of x, this is a cube root function, not a square root function, so you might have to look at it on Desmos or on your calculator to see what it looks like. But once you did that, you would see that the graph looks a little something like that. It's a terrible drawing. But its range, since it's not stopping anywhere, is from negative infinity to infinity. There's no horizontal asymptotes here for us to worry about, which means that I know that that purple interval that I wrote there is going to be the domain of my final answer. Okay, but let's go ahead and switch these x's and y's so that we can see what the inverse function would be. So I'm going to have x equal to the cube root of y plus 2. I'm going to cube both sides to get rid of the cube root, and then subtract 2 from both sides to isolate the y. That means my inverse of f is x cubed minus 2. And without having to do much thinking on what the domain is now, I already can answer that the domain is from negative infinity to infinity, because that's, again, the range of my beginning graph. Okay, so the steps here are make sure you know the range of what you started with, switch x and y, resolve for y, and then use that same range as your new domain. Okay, this one has some wild amounts of algebra, and it's actually a really, really cool example. So I want to make sure, one, that you had a nicely written example of it, and two, let's talk about it. So if we graphed f of x, first of all, you should know it's going to be a rational function, which means that the denominator can't be 0. That would be my vertical asymptotes. But if I'm asking about range, I need to know about my horizontal asymptotes for this graph. That's just something that rational functions have. We would either use Bobo, Botten, or Eats DC for this. This is an Eats DC question because the exponents are the same, and the coefficient of the leading coefficient at the top and the leading coefficient at the bottom are both 1. So we know we have a horizontal asymptote at y equals 1, which means that this graph shows up everywhere except for 1. That's the range of that beginning f of x function, so no matter what, we know that's our domain. But if you look at my work here, changed f of x to y and then switched all the x's and y's. I want you to write down every step, like with the words of what I did here, because this is some cool algebra, and I just want you to be sure that you know what's going on. From the first step to the second, all that I did was multiply by the denominator. I'm going to multiply both sides by y minus 3. It will cancel out the denominator and be multiplied on the left-hand side. Then I distributed the x. In this next step, I did two things at once. I added 3x to both sides, and I subtracted y from both sides. The reason I did that is because I wanted to get all of the y's on the left-hand side, which now you see over here. This next step can kind of throw us to a loop, so let me kind of zoom in right here so you can kind of see what's going on. If we have xy minus y, if I take out the GCF, both the xy and the y have a y in common. So I can kind of divide away, undistribute the y's basically, and put them in front, which would mean that we have x as a leftover and minus 1 as a leftover. So it's reverse distribution. It's called factoring out the GCF, but sometimes if you think of it as reverse distribution, it kind of helps. So that's what I'm going to write down because I think it's helpful. Reverse distribution. The next step is to divide by that GCF's leftovers, basically. So we're going to divide by x minus 1 on both sides, which means that we have now isolated our y. And that's my inverse function. And again, without having to do much, I know that my domain is negative infinity to 1 and then 1 to infinity because that's the range of what I started with. But this also makes sense because we know that in a rational function, x minus 1 can't be 0 for a domain, which means x can't be 1. And that's exactly what we're saying here. All right, now it's your turn. We have D here, and you have a nicely worked out example for this particular type for the rational functions. I want you to pause the video and give it a shot. So let's talk about this one. So if we have the function and we're trying to find its inverse, first we need to talk about the range of f of x, the one that's already given. Since this is a rational function, I know it's going to have some weird breaks in it. This one would have a horizontal asymptote and a vertical asymptote. And since we're talking about the range, we're more interested in that horizontal asymptote, the flat line. We have to decide if this is Bobo, Botten, or Eats DC. And this is an Eats DC, which means we're going to divide the coefficients. That's 2 divided by 1. So I have a horizontal asymptote at 2. And a vertical asymptote at negative 2. So my pouring skills are going to look terrible right now, but let's say it looks something like that. Ew, so ugly. Okay, we know that if that is what the graph looks like and it has a horizontal asymptote at 2, that means it goes from negative infinity to 2 and then from 2 to infinity. That's the range of f of x, which means it's also going to be the domain of f inverse. Okay, let's find the inverse of f. which means we're going to substitute in, well, I like to plug in a y just to get started. Then we're going to replace or substitute every y with an x and every x with a y. To help you guys out, I'm going to show all of my steps here in red, and I'm going to show lots of steps. The first thing we're going to do, I just realized I wrote an x right there. That should be a y. Stop me when I'm doing something crazy. I'm going to multiply by that denominator, y plus 2 on both sides. Because again, I'm trying to solve for y. That cancels out my denominator, and I have x times y plus 2 equal to 2y minus 1. I'm going to distribute the x, which means I have x times y plus 2 times x equal to 2y minus 1. I'm going to show this next part in 2 steps because I think I lost some of you on the last one. I'm going to subtract 2x from both sides. That would give me xy equal to 2y minus 1 minus 2x. And because I'm trying to solve for y and get all the y's on the same side, I'm going to subtract 2y from both sides. Okay, that means I have x times y minus 2y equal to negative 2x minus 1. Now, the y's are on the same side, so I want to get them to be written similarly or as one piece. So I'm going to factor them out of that binomial, which means I have x and a minus 2. That's reverse distribution. It's factoring out the GCF. And very last, I can divide by this binomial x minus 2 to isolate the y so that I have y equal to negative 2x minus 1 over x minus 2. And that's the inverse for my f of x function. Now, before I'm done, though, I also have to talk about that inverse function's domain. But we already know the domain because we found the range of my original function, f of x. Exactly what we have as the range becomes the domain. And this range makes sense to us, again, because our final function here is rational. That means we know that x minus 2 can't be 0, that denominator. Which means also we know that x can't be 2, which is like literally exactly what this says. So this is where it really gets important that you've taken the time to look at the range. Because if you notice, my f of x function is a square root function, which means it has some restrictions on its domain and range. For f of x equal to the square root of x minus 4, I recommend graphing if you're not that familiar with what that transformation does to the square root function, but it's going to look something like this. Okay, yes, the domain has changed because the domain can't be, that x minus 4 can't be less than or equal to 0, which is why it stops at 0 here. But my range is affected as well. This range is from 0 to infinity. Okay, which means that when I'm done, even if my final function doesn't have that restriction like it had a little bit ago with that rational function, we have to include that domain or that range in my domain. So we look at this step, just kind of following along. We change f of x to y, we switch x and y, we would square both sides, we would add 4 to both sides. We've got our inverse function. If you notice, this is a quadratic. So if I were to graph this right now, it would look a little something like this. But because we're actually trying to make sure that this quadratic is the inverse of what I started with, we have to make sure we're only talking about the graph from 0 to infinity. So not this side. Now, if I were to graph both the original function and the new function, it would actually be a reflection across that y equals x. If I still had this part of it, it wouldn't. But by adding in that restriction, that domain, that was the range of the original function, we have actually kept them as inverses, which is really cool. Okay, pause the video. I want you to try the next one. Find me the inverse and tell me its domain. Okay, hopefully you did. Let's look at this one. So if we want to do the range of f of x, this function is another square root function. It would look a little something like this, where again, the graph has a boundary, has a bottom or lowest point at that 0, from 0 to infinity. That will become the domain of my answer, even if that restriction isn't part of the normal, I'm using air quotes and you can't see me, normal inverse function. So let's go ahead and find it. So we're going to have x's and y's. They're going to switch the position of x's and y's. We're going to square both sides. And we're going to subtract 5 from both sides to solve for y. So my inverse function is x squared minus 5. But I have to include the domain that this graph only shows up at the range of my original f of x function, because just like a second ago, this would have been a quadratic that looks a little something like this. For this to be the inverse function, we cannot have this side of it. Now it actually does look like a reflection of that range of that f of x function without the stuff on the left side of 0, from 0 to infinity. Now here's why we spent a class period on composing functions, because once we have inverse, we also have to verify that the two functions are actually inverses. And the way that we're going to verify is we're going to go back and use the definitions of what inverse functions are. So we say that two functions, f and g, okay, f and g, just we'll make them red and blue like we did when we did function compositions, are inverses if and only if we can do f of g of x and it simplifies down to literally an x, and if we can do g of f of x and that also simplifies down to just an x. So to show that the functions are inverses, that's what we're going to do. We're going to show that f of x can be composed with g of x, and both times they simplify down to 2. Sorry, not 2, x. So if I'm doing f of g of x, that means g of x is the inside function. Do either f of x or g of x here have any restrictions on their domains? No, they're both from negative infinity to infinity, so there'll be no carryover restriction here. So we would do f of 4x plus 8, which means that's what I'm plugging into that f function for x. So instead of x, I write 4x plus 8. This is just a simple distribution problem. 1/4 times 4x, that's just x. 1/4 times 8, that's 2. And then x plus 2 minus 2 is just simply x. Halfway there. Just because we verify one doesn't mean we verify both, so let's make sure that the other one works as well. This is going to be g of f of x, so g of 1/4 x minus 2, which means we're doing 4 times the input plus 8. The input this time is 1/4 x minus 2. We distribute 4 times 1/4 is x. 4 times negative 2 is negative 8. Bring down to plus 8. And that, again, simplifies to x. This math here, showing that f of g of x and g of f of x both simplify down to x, allows us to verify. We know now officially that f of x and g of x are inverses. We verified it. Woohoo! So let's try one. We're just going to be plugging these numbers in. These have some crazy amounts of algebra in them as well. So hang on, we're going to get it. We have f of x and we have g of x. And so we're going to compose both of them to see if we can reduce it down to x. So if we do f of g of x, that means that I'm going to be plugging the g of x function into f of x, anywhere you see an x. So f of x looks a little something like this. We've got x plus 7 and x minus 3, but both of those x's are going to be that function, which means we've got fractions in our fractions, and we're going to have to deal with that. So what we're going to do to deal with this is we're going to multiply both sides, both the numerator and denominator, by x minus 1, because it will get our fractions out of the denominators. This in the numerator, the first term of the binomial and denominator cancels out, and then the second just gets multiplied by x minus 1. Same thing happens in the bottom. Then if we just distribute and continue to simplify, this is 3x plus 7 plus 7x minus 7. I just distributed the 7. 3x plus 7 minus 3x plus 3. I find my like terms and I simplify them. These will cancel. That leaves me with 10x. And these will cancel. That leaves me with 10. And 10x divided by 10, that's x. That's what we want. Now, we're not done, though. All we've done is halfway verify this. I want you guys to pause the video and try to compose the other direction, g of f of x, to see if that reduces down to x. Hopefully you pause the video and we're good to go. So if we're doing g of f of x, that means that we are doing g as the outside function and f as the inside function, which means that I'm going to take g, which is 3 times x plus 7 and x minus 1, and instead of x, plug in the entire function x plus 7 over x minus 3 for both the numerator and the denominator's x. And we've just got to simplify because that is way too complicated to leave. So we're going to multiply by that denominator in both the top and bottom to get our fractions out of fractions. That means we're left with 3 times x plus 7 plus 7 times x minus 3. The denominator of the first part cancels out. That's why we did this. Then we have x plus 7 minus 1 times x minus 3. A whole lot of distribution happening here. This is 3x plus 21 plus 7x minus 21, and then x plus 7 minus x plus 3. Combine all my like terms. These 21s cancel, so again I have 10x in the numerator. These x's cancel, and I have 10 in the denominator. Oh, look! We reduce back down to x. Since both g of f of x and f of g of x reduced down to x, these have been verified. We know that they are for sure inverses. So what that means we're able to do is find and verify an inverse. So we're going to do this question in two parts. They've only given me f of x. My job is to figure out what that inverse function is, and then make sure that we got it right, verify it. Okay, so first things first, let's check on the range of this function of f of x. It's a rational function, which means we know it's going to have a horizontal asymptote. And that horizontal asymptote, since this is an each DC problem, appears at 1. So my graph looks a little something like this. Ooh, nope, that's horrible. Okay, that's better. Not really. Pretend that's all right. So since I have a horizontal asymptote here at 1, my range is going to go from negative infinity to 1, and then from 1 to infinity. Cool. I already know the domain of how I'm ending. It's got to break at 1. So So let's go ahead and find the inverse. We're going to switch f of x with y, since those are the same thing, and then switch all of the x's and all of the y's. Multiply by y minus 2 on both sides. Distribute. Subtract and add. Sorry if you hear our dogs barking. I'm going to factor out the y and then divide by y minus 1 on both sides. Look at that crazy amount of algebra we just did. Love it. So the inverse of f is 2x plus 3 over x minus 1. And my domain, I already know, I don't have to do anything extra. It's from negative infinity to 1 and from 1 to infinity. Because that's the range of f of x. Okay, well that's all fine and dandy. We've found f of x. But now we have to verify that they're actually inverses. So we're going to take this paper to the side and we're going to have this inverse of f function be my blue to the red so we can verify this using function composition. So we're doing f of g of x, which means we're going to have f on the outside, and the input that we're substituting in is 2x plus 3 over x minus 1. Cool. So we have x plus 3 over x minus 2, but both of those x's are going to be this entire equation. We'll multiply everything by x minus 1, which means we have 2x plus 3 and then 3 times x minus 1. And then 2x plus 3 minus 2 times x minus 1. Just getting rid of the denominator by multiplying it to everything. Do some distribution. That's 2x plus 3 plus 3x minus 3. And 2x plus 3 minus 2x plus 2. We combine all our like terms. That's 5x and then 5. Oh, look. We got an x. That's half of the verification I need. I still need to compose it the other way, g of f of x, and make sure that that also works and gets me back to x. And then I can verify and be done that these, not only did I find the inverse, but that I verified it. So that means we're going to take the g of x function and plug the f of x function into it. Okay, so let's do that. We have 2 times x plus 3 and then x minus 1, but both of those x's are the input of f. This time I'm multiplying the top and bottom by x minus 2 because that's what's in the denominator already, which means we have 2 times x plus 3 with no denominator and 3 times that denominator. And we have x plus 3 with no denominator, and then negative 1 times x minus 2, which was the denominator. We distribute like crazy. This is 2x plus 6 plus 3x minus 6, and then x plus 3 minus x plus 2. Combine all of our like terms. We have 5x over 5, and voila, we're back at x. We have verified that f and what we found as the inverse of f, which I started calling g, are inverses. Okay, so what I use this as the g of x function so we could compose them and verify that f given in the problem and the inverse of f that we found are actually inverses of each other. So much algebra, so little time.